Pleiades, all these things.
Isn't that just because of the tilt of the Earth, which is why we have the seasons?
Partly the tilt, but mainly because of and the tilt gives us how high the Polaris is, for example. Let's see. The tilt basically aligns our axis where it is, and how high we are in latitude determines how high that is going. So the rotation of the Earth gives rise to this nightly motion, but then there's a yearly motion due to the orbit. So let's see if we can get a picture of that. So I'm going to skip down here a little bit. Here we have the sun and the Earth. We're around here in late August or mid-August. But let's sort of take things as they are here in June versus December, for example. Now here's the sun in June. Then if we look midday, the sun will look like. Of course, you don't want to look directly at the sun, but if you observe it and you know where you can get an idea where it is in terms of the celestial sphere, then it actually is in Gemini. That is, if you were able to get rid of the brightness and see the stars, you would see it's in Gemini. But at the same time, when you look at the night sky, you're looking the opposite direction at midnight, out here. And so you see in the night sky at midnight, you might see Sagittarius and Capricorn. This is the zodiac, and basically you see things along the line where the sun has an apparent path of travel. So during the day, the sun goes up, sets, it rises, sets. But during the year, as it goes through the celestial sphere, it has a certain path. That path reflects the plane of the Earth's orbit. So it looks like we're sitting here and the sun's going around, but we're actually going around the sun.
So basically, like in March, if we looked up at the night sky, would see Virgo and Leo?
Yeah, so at midnight, you might see Leo
right.
and Virgo.
I see, okay.
And that would be where the ecliptic is, and the ecliptic has a certain height. Now the tilt of the Earth causes this path of the sun, or apparent path of the sun, to tilt relative to the equator. And I wonder if we have a picture that can show that here. This doesn't show it. Let's see if we have something else going. No, maybe I'll maybe I can describe it. If you look at the celestial sphere, you have the equator, and if you use the night sky where we are now, then if you're actually, well, let's think if we're on the equator, then we're looking straight up at zenith, and the equator goes out and it goes right from east directly overhead to west. And if we're looking east, then up there is north, and down there is south, and that's where the north celestial pole, the south celestial pole would be, right there. Now we could walk north that way. Now as we walk north, then things would look like they're tilting. So after a while, 10 degrees north, everything would tilt 10 degrees that way, relative to us. And then another 10 degrees, that's 20 degrees. And if we come all the way up here, we're up 38 degrees north latitude. And so the north polar, north celestial pole, and the Polaris, for example, would be at where you are in latitude, 38 degrees height. And there would be 38 degrees distance, or the angular distance from the zenith down to the equator. So it goes from 90, take away 38 is what? How much?
67.
Maybe
57.
52. See, it's 60, but it's almost 40, so it's just about 52. So 52 degrees above the southern horizon, that's where the equator is at its height. And so the equator here goes from the east up to 52 degrees and down into the west. Now, the ecliptic has an angle relative to that because of the tilt of the Earth. That is, the axis is off, you know, and so therefore, when we let's see, how should I put it? Here's the Earth and here's the sun. So if we look at the sun, basically here's like the equator, but the sun has a certain angle relative to the equator. So the celestial equator would be out here. And in June, we reach the summer solstice. There's a certain angle between basically due to the tilt of the Earth's axis relative to a perpendicular to its orbit. How much is that tilt, do you know? 23.5 degrees. Basically, it's reflected in the fact that at the Tropic of Cancer and the Tropic of Capricorn, at the solstices, the sun is directly overhead. So, the tropic, I don't know if this is the Tropic of Cancer is the north, I forget. Yeah, maybe. So therefore, if you're there, the sun is directly overhead at the solstice. That's 23.5 degrees. So if you see the equator, then you should be able to calculate well. In the winter time, then the sun is very low, but in the daytime, so that means the ecliptic would be very high in the nighttime. Or in the summer, the ecliptic is very high because the sun is very high. But then the ecliptic at the night, the ecliptic would be very low. And if you look at the night sky, basically all the planets and the moon follow roughly along that ecliptic. And if you go out tonight at about 8:30, you'll see three bright objects off in the southwest. Two of them are planets. Saturn and Mars are conjunct right above one another. Saturn above Mars. Below that is a twinkling star. That would be Antares in Scorpio. It's quite a sight. You get a telescope out, you can see the Saturn's rings and stuff like that. Yes, go ahead.
Is it possible for the Earth to get rotation locked to the sun, like the moon is to the Earth?
Is it possible for the Earth to get what?
Rotation locked? Like,
Rotation.
because the moon doesn't spin on its own.
That's a different story. Okay, so we'll talk about resonances later. The moon is always facing us. It orbits once for every time it rotates. It's a one-to-one resonance. I don't know. I suspect no. It takes a certain amount of time for that kind of thing to happen, and often the time is shortened by proximity. The proximity of the Earth and Sun is not enough to avoid getting gobbled up by the sun as it dies out before it might lock tidally. But that kind of thing happens all the time. Mercury has a kind of tidal locking in its orbit. I think it's what is it, 2-to-1 resonance, I think it's 3-to-2 resonance, I forget. And some of the moons of Jupiter do, because such a powerful force of gravity, the moons are so close they get tidally locked and stretched. Okay. Was there other questions? I thought I heard maybe something. Okay, so there's something called so let's just list these things that we've been talking about. So the celestial sphere. Say there's the equator. I'll call it celestial equator. When I prefix it with C, it would be a celestial. Celestial North Pole, South Pole. There is the let's say, I should say, ecliptic. Now the ecliptic is at an angle. Let's see. I'm not sure exactly where it starts. But let's just say it executes, so it's another plane, it's another great circle, it's tilted. And when it tilts up here, it goes through the equinoxes, basically the sun's path. Say, when it's in the northern hemisphere, when the sun gets very low, that's winter. And then when the sun gets very high, that's summer. And basically those are called the solstices, where the sun is at the lowest in the sky or the highest in the sky.
Also when the day and night are equal, isn't it?
That's the equinoxes. So right here, when it splits the day into two equal parts, and two equal parts, the equinoxes, 12 hours night, 12 hours day. And the celestial spheres, should I say, it's grid, the grid of right ascension, which is like longitude, it begins at the vernal equinox. That is, at the position of the vernal equinox is 0 in right ascension. And then there are 24 hours of right ascension as you go around. And the sun basically, the earth basically rotates through that. And we get, for example, 0, and it's like a clock. 0 hours, 1 hour, 2 hours, 3 hours, up to 24-hour clock. And basically the sky, you can split with something called a celestial meridian. The ecliptic, maybe I'll put down as the apparent solar path, but actually the plane of Earth's orbit. There's a celestial meridian, and that's sort of fixed to where you are on the Earth. And basically, you've got zenith, and let's see, going from north through the north celestial pole up to the zenith down the south. It's called the celestial meridian, and basically all the stars will rise and set, pass through the celestial meridian. And when a star passes celestial meridian, its right ascension at a certain number of hours. We call it transits at celestial meridian, and that is the celestial time or sidereal time. So you have something called sidereal time. There's solar time and sidereal time. Sidereal time has to do with the stars and relative to the stars. The Earth is rotating and orbiting at the same time. And so a solar day is basically when it is the time it takes from the sun being at, for example, at one position in the sky like sunrise, or at the apex in the sky midday, to the next day. That takes a certain amount of time. That is 24 hours exactly. Okay, so that's a solar day. So a solar day. However, if you, let's see, I can get a picture of this in my phone. However, here, for example, here's the Earth looking up, say midday, to the sun at its highest point. And it takes 24 hours to get back to that point. But notice that the Earth has gone through its orbit. It's going around the sun. And so if you look straight out parallel to the way you were looking relative to the stars, the sun isn't quite at that same point. The stars are at the same point, but the sun isn't, because you moved relative to the sun and the stars, so the sun looks like it's moved. Once around relative to the stars is the sidereal day. Now the orbit is this way and the rotation is this way, so it takes a little bit more time in orbit for this revolution to catch up and make the solar day. So the solar day is a little bit longer than the sidereal day, about 4 minutes. Sidereal day is 23 hours and 56 minutes. So we also talked about the sidereal clock or 24-hour clock. And that's when the respective stars pass the celestial meridian. Okay, let's see. Now, as we said before, let's see, it's summer and winter. So let's just go back to the zodiac here. If we look in the night sky, in the summer, we see these constellations. Right now, we see these constellations, including the summer triangle and stuff. But as the year goes on, if you look down from the North Pole to the South Pole of the Earth, and by the way, all the planets all orbit the same direction, counterclockwise as you're looking down on the North Pole of the Earth, for example. So the Earth is going around here, and then later in the year, we see other constellations along the ecliptic. This is called the zodiac. Zodiac is just constellations the ecliptic goes through. And so in September, we'll see, say midnight, see Pisces along the ecliptic. But way in December, we'll see Gemini at midnight along the ecliptic. So you see different constellations at different times of the year at midnight, or at a particular time of night, so you see different stuff over the year. And you go around once, and then you see the same stuff. Almost. Fact is, the Earth's axis is not quite fixed. The Earth is like a spinning top, and when you spin a top, it sort of wobbles. So the Earth is actually wobbling due to the influence of other planets, sun. Basically, it's a tidal force. Someone mentioned somebody mentioned tidal locking or something. So it's a kind of tidal forces affect the Earth, and so it causes it to precess. So the Earth's north celestial pole, or North Pole, and therefore North Celestial Pole, changes over time. And it goes in a big circle once every 26,000 years. If you've heard of the Mayan calendar, that's the great cycle time. 26,000 year cycle. Yeah, the Mayan calendar. So the North Star won't be Polaris after a while. Maybe a few thousand years ago it was a star called Tuban, and maybe I forget how many years it will be Virgo. Let's see if there's a picture of that. Yeah, here. Yeah, there you go. And Lyra. So basically, the Earth's pole is precessing, and in 26,000 years, we'll make a great circle and come back to Polaris. So what does that mean? That means that Earth's tilt in 13,000 years will be opposite in the direction of the sky. That means the summer constellations we have now will be the winter constellations then. The winter constellations we have now will be the summer constellations. So that will change. And in fact, every 26,000 years, you go through a whole cycle in the zodiac. So that means for every 2,000 years, you migrate one constellation. Now the time of astrology, not astronomy, I'll just finish up. In time of astrology, back in the Babylonian time or before, that was 2,000 years BC. Then all this stuff on astrology was based on that. So all your birth signs, they were based on that stuff 4,000 years ago. We're off 2 signs since then. All the astrology is off by 2 signs. Just in case you wonder.
Is that why when it kind of pointed up, Scorpio was like in June, I think?
I don't know. I don't know.
It's on a
from-
different
from
page.
this diagram, but,
It was on a different.
yeah, yeah, well, that has to do with the orbit of the Earth. This has to do with, what is summer and what is winter in terms of the constellation. So the actual, the tilt would be different.
Okay.
Summer would be summer, but you have different constellations.
Okay.
Okay, everybody, so, let's see, just hand in your exercises. You just really finished, so, let's make this homework due Thursday.
That sounds good to me. It's basically odds for the odd matches at the end. They'll have like at the end of the chapter they'll have like a random thing. It's just all we gotta do is just ask questions. And we're supposed to go through this all through class and everything, and basically be able to answer. That's why we gotta take all these.
Multiple choice question.
I don't know. That's actually a good question. I'm gonna have to. I think he
Because
said.
there's like 4 different sets of questions.
I think he said yes, but don't quote me on that.
Get this.
I gotta write my name on it. I gotta write my name on it.
They're all the same, the odd review and discussion, all the same.
What's Thursday?